internals good on databases. So people who ask good questions get a chance to get a copy. So there's that. So hi folks, I'm Alex Petrov. I'm Apache Cassandra committer and a PNC member. And today I would like to talk about queue depth, backpressure, and deadlines. Even though I've used load balancing in the subtitle for my talk, what I really want to talk about is cluster stability and workload fairness. Load balancing is somewhat overloaded combination of words, and more often than not, one thinks about load balancing in terms of like a thing that sits in front of the database rather than in the database itself. So we'll talk about how deep our queues can get today, how deep they could have gotten just a couple of months ago, and how deep we think they should be able to get in the future. We'll talk about the backpressure, what we do now, what we have tried, and why some things have worked better than the others, and some things that are still missing and we can get improved. And lastly, we're going to talk about deadlines and about how we can configure them and about wording ambiguity that has led to some trouble. So first, let's set some expectations for this talk. What specifically are we going to take away from it, and what problem are we even trying to solve? So currently, on the coordinator side, all the requests are processed by a single native request queue and in first in, first out order. While this is a viable strategy for like normal circumstances under heavy load, this approach starts to show cracks and can potentially lead to avoidable elevated latencies, query timeouts, and in worst case, cluster instability. There are different efforts in Cassandra community to improve the cluster performance specifically. So what I'll be talking about here is primarily relating to fairness and minimizing latencies, making sure that if we decide to shed part of the load, a number of requests that will be not processed is going to be minimal. And we'll discuss whether we can find ways to process requests optimally, at least to some definition of optimality, and minimize negative impact of interactions between queries. And while Little's law says that we cannot minimize queuing time for all items in a system, we can still find a way to decrease time for some of the items by making the workflow a little bit more fair. And we will try to achieve fairness by avoiding workload imbalances and ensuring that all clients get a fair slice of the workload. And we will also try to avoid utilization imbalances, where some nodes get overloaded while others might be idling or experiencing substantially lower load. And of course, all of these things are achievable only to a certain point, but implementing them will make operators' life much better. So conventional wisdom says that one scales through sharding and replication, but we already have known that a while ago, and Cassandra has been built with these things in mind. Unfortunately, there is a little advice about what one can and should do when the cluster is overloaded. Somehow, this subject is avoided when not really often discussed. There might be some retrospectives about how different projects have dealt with some issues, but unfortunately, I could find very little systematic research on the subject. But I've tried my best to put together whatever little I could find. So one piece of advice I often hear in the Cassandra community is to use a token-aware load balancing strategy on the client. This sounds like a great idea because we're reducing load by not having to issue a read or write to the local coordinator local replica. But of course, this also means that if the target replica becomes hot, having coordinator load in addition to the replica work already done by the node isn't making scaling it easier. What if we could use token aware, but have an automated way to switch it and diversify coordinator load and temporarily exclude the nodes from being considered for coordinator? I also feel that there has been a bit of a disconnect between the client and server development. Gladly, we will now control and maintain at least some of the drivers under Apache umbrella, which is a great step in the right direction, but I think we should explore more client-server protocol interactions, and yeah, some of them can be beneficial. So distributed system is going to be as strong as its weakest link, and by neglecting any part of the system, we're leaving improvements on the table. So my favorite example of a decision that was made by the client developers that has become an implicit default for Cassandra is going to be discussed in this talk in quite a bit of detail. So lastly, I was thinking about some configuration options. So we have configuration options galore. How many? Two and a half lines of YAML, right? But I feel there is a big disconnect between native transport max threads for which we're not setting any default value in Cassandra, but then we default to 128 in the code. But then we have 8 multiplied by the number of cores default for read and write stage concurrency. But like the default in code is 32 threads. So these threads serve very different purposes, right? So native and read-write. Native is mostly idle and waiting for responses from replicas, and read-write stages are performing actual reads and writes. So it would be ideal to make this configuration more straightforward and perhaps automatic. To set up the stage and mention why I even started thinking about the subject, I'd like to tell a story of a bug that was actually not a bug, but rather an emergent behavior arising from interaction of multiple subsystems. This behavior was present in Cassandra for a while, at least ever since we've made our native queues unbounded, and unless you have pulled in the changes, your cluster might be prone to this issue too. And John has summarized this very well, and he promised to help me with the voiceover for this slide by reading it in his own voice.
You got it. When a node is under pressure, hundreds of thousands of requests show up in the native transport queue, and it looks like it can take way longer to time out than is configured. You should be shedding load much more aggressively and use a bounded queue for incoming work. This is extremely evident when we combine a resource-consuming workload with a smaller one.
So let's try to take this one apart. Thank you so much. John is saying that we should be using bounded queue for incoming work. So while this is a great idea in principle, who can say how are we going to size this queue? How many requests should we allow in the queue before we consider it full? Why have we even switched from bounded queue several years ago to an unbounded one? And there has been a configuration setting which was called max queued native transport request. Like, what happened to it? So essentially, in Cassandra 15.0.13, native queue became unbounded, and this configuration setting got removed. So in this ticket, one of the authors, unfortunately not present here, and otherwise I would ask them to read it, said, we have a world where clients have been depending on the server, trying its best to never push back. So they have inadequate queuing models internally with no support for noticing or handling the backpressure. Quite interesting, right? And later, I'm going to be slightly paraphrasing for brevity. This is, to me, a design flaw that should be designed and addressed in clients, but we could mitigate it for now by making the native queue unbounded and simply tracking the total number of bytes we have read off the wire but haven't answered. Perhaps we could even make the behavior of overloaded exception. So far so good. It was quite a few years ago, and it got into this load shedding territory. So we'll take a note of that. And later, John is also saying a super important thing. So he said, this is extremely evident when we combine a resource-consuming workload with a smaller one. So let's put a pin on it, and we'll come back to this. So it could be convenient to have some form of a bug that has caused this behavior. But unfortunately, this was not really a bug. This was just a combination of different behaviors that were coming together or resulting into something unexpected. So when client starts to request, it also starts a timer. By default, in 3.x driver, this timer is 12 seconds. When the request arrives on the coordinator, it lands in the native request queue. It will sit there for a while, and then the coordinator is going to start execution. On the coordinator side, we also control read and write timeouts. However, these timeouts are going to only start when coordinator starts sending requests to the replicas. So the cluster becomes overloaded. The replica responses become slower and slower because replica side queues start getting backed up. And eventually, timeouts for coordinator queries start crossing this 12 seconds boundary. However, since from the coordinator's perspective, timer has to start only when it starts sending the request to the replicas, it carries on with execution. So all replica queries stay within the configured timeout boundaries, but the responses arrive to the client already after the client has stopped listening. Coordinator starts speculating on reads, clients start retry and timed out queries. This all further exacerbates the problem since we now may have more than just one version of the same request waiting in the queue being executed. Queries are allowed to stay in the system almost perpetually, or at least were prior to this issue. And in many cases, they would have been allowed to run for a very long time after the timer for client has expired. So solution turned out to be relatively straightforward. Limit the time request time for which the request is allowed to stay in the system. We've introduced the so-called native request deadline, after which it simply makes no sense for coordinator to even start processing the request because the client handler for it has already been removed. We've inspected the code base and found that local read runnables didn't respect timeouts at all. The same thing was happening for the remote mutations. So as long as the message has reached the replica, mutation would have simply been applied, no matter how long it took. So after fixing this, we've seen a substantial improvement in the number of success responses and substantial decrease in the number of timeouts. So the cluster was not only now doing more, but also producing more successful responses than it used to. So successes and timeouts were reported on the client side. However, before this patch, many of these timeouts would have not even been reported on the server side. Since previously timers were started only when coordinator dispatched the replica request, any coordinator request capable of collecting replica responses within the configured timeout would have been considered successful, even if it has finished after the client has stopped listening. So we have solved the problem by simply dropping or shedding some of the requests, but we should be able to do even better. Number of successes should have been even higher, and number of the timeouts should have been even smaller. Now let's get back to the meaning of the timeouts. Since depending on how you interpret what timeout even means would have large impact on how you're implementing them. So last year I've done a little survey of what some of our configuration options mean for different people. And what would you think? There are almost as many opinions as there are people. The simplest answer to the question of what read request timeout is simply how much time the single replica takes to respond to the coordinator. But wait, most of our requests involve more than one replica, and some operations, namely writes, may live inside of the system after the coordinator has responded to the client. Yeah, we will be blocking more often than not on responses for the majority of the replicas, but we still issue writes to whatever the replication factor is considered to. Moreover, when you're looking at your metrics, what are you looking at? Like coordinator request latency, replica request latency, local request latency, all three of the above. Which one is more important? Okay, maybe it is way too philosophical of a question, but at least we need to have a good understanding which one is closer to the configuration option that we are setting. The coordinator replica round trip time sounds like a simple thing, but it already consists of several major components. So who thinks it's 2 components? No? 3? 4? Anyways, I know it's like a little arbitrary and it depends on where specifically you're gonna slice it, but let's for a moment imagine that we only care about and therefore only start our measurement when the request has started traveling from the coordinator towards replica. So that's gonna be 1. So do we start the processing of the request on the replica side right away? No, not really. It first lands in the queue. That's 2, right? Of course, most of the time the queues are empty, but we wouldn't be a highly available database if we only cared about the happy path. So request sits in the queue for a while, and only then can we get to the local request latency component. That's 3. This is arguably the most important and interesting part of the query, since that's what performing the read or write itself. And after the replica knows the outcome, it needs to communicate it back to the coordinator, and that's 4. So at least 4. So that's all good. But let's imagine a situation. So you have a spike in write request latency, and you are starting wondering, what does it even mean to have a spike in local request latency? How does it translate to the coordinator request latency? Which part of the system does become suspect? Why all of a sudden it's getting so complicated? Now, while on the replica side, we did say that the replica does not simply start processing the request first spends time in the corresponding queue. The same thing is going to happen on the coordinator side. After coordinator has created the outgoing message, it will put it on the queue and will spend some time in the outbound queue before it even reaches the network. But that's not all of it. Coordinator itself also is performing some work. However small the portion of this work is, it's going to be parsing requests, figuring out how to route it, and what's the appropriate replica set, and so forth. But besides the coordinator outgoing queue, every request from the client is going to spend some time in the native queue. And because this queue is sort of like a largest fire hose, it is also most prone to clogging most of the time. So any hiccup downstream means that we'll be pulling off this queue slightly slower, and the number of requests on it, pending requests, is going to start growing. So interestingly, local request latencies do not vary that much, even in the cluster that is not super stable. And local requests are largely limited by concurrency, and there is not much that can make them slower. So maybe a GC pause here and there, but to be honest, garbage collected languages get more criticism that they deserve. So a factor that has a larger impact on cluster stability and latencies is queuing. Every microsecond the request spends in the queue, it's not being worked upon. It's time that will be added to the request during which no work was done for this specific request. So requests can sit in the queue disproportionately longer than they are processed, and unless you're taking queuing into consideration when computing request timeouts, you're measuring the wrong thing. So if the client considers request to be timed out after 2 seconds, and the server only counts the 2 seconds of the coordinator replica round trip time, the server is going to be under-reporting the timeouts. From the client's perspective, every request for which it did not receive a response within the 2 seconds is considered a timeout. But from the server's perspective, every request that it was able to start and finish within 2 seconds is considered a success, disregarding the queuing time. So 3.x, a series of Java driver, has a configuration option called read timeout, but surprisingly, it does not control Cassandra read or select timeout. But it controls the socket read timeout. In other words, how long the driver waits for a response from the given Cassandra node before considering it unresponsive. This is an understandable thing, and I think that the primary reason for that is that there is no distinction between read and write queries from the client. It's just like a blob of text and some values that it's going to be interpreted by the server. This is, however, not an excuse not to draw any distinction for the same thing on the server side. Let me get this straight. Even though we did have a configuration option that made it appear as we have distinction between read, write, and rage timeouts, this distinction applied only to replica requests. Let's say we have a timeout of 2 seconds, and every individual replica request timeouts completes in just 1 second. Technically, we're doing what we are asked to by not timing them out, But as soon as we start getting more requests in a single second than we can process in a single second, the queue size is going to start growing, and eventually requests may end up spending 5 seconds in the queue, and we will still not be timing them out. So you might be saying, Alex, it's all semantics, nitpicking, and stop catastrophizing. And I sort of like agree with you. Like on a happy path in your development environment or in a stable cluster, coordinator replica round trip will be dominating. But as soon as there is a burst of traffic, I do not want the cluster to tip into the death of spiral from which it can recover only by the operator intervention. So let's summarize. So when computing the total request latency, we as database developers should make sure to include queuing times, which is in our case, the time client spends in the native queue, the time replica request spends in the coordinator outgoing request queue, and the queues of the read or write stages on the replica side. We do not always have access to client as database developers, so sometimes we may end up not knowing exact time it takes for the request to travel from the client to us. Gladly, more often than not, this is not that important, and when we can live without that detail. However, when setting up a deadline, in other words, a time after which the client will consider request timed out for the request, we absolutely need to know when the client is going to do that. So something we really did not want to include in this patch is making some form of a hard limit, a number of requests that the operator has to sort of like figure out magically in order to say that this is like the maximum number of queued requests on the coordinator side. So even after the extremely careful consideration, one can barely make that call, at least I can. Every operation can potentially be unique, and even if we do know like exact numbers for majority of our queries, this approach is way too prone to errors. Instead, we have decided to use request concurrency and timeouts as naturally imposed bounds for the query. We'll try to serve as many requests as possible and then shed the rest of the request. The rest of the talk is going to try to figure out what this rest is going to be. So why are queues such a big problem? And why is it important to take queuing into consideration when developing a distributed system? So let's say we have a simple setup, 10 threads. Each request coming spends 10 milliseconds, it takes 10 milliseconds to process. That means that each thread can process 100 requests a second, or we can process 1,000 requests on 10 threads in a single second. Now let's say we suddenly face a 10 times more requests in 1 second than we usually do. If we process requests in first out manner, we won't get to process the request that has just arrived until all the requests that have preceded it are executed. So if we are at capacity with 1,000 requests per second, now we'll just increase the latency of all the subsequent requests because there is just no way for us to catch up. So if the server is working at a capacity, there is not much that we can do to return to the not normal latencies and normal number of pending requests in the queues. And yesterday, Jordan even said that at Netflix, they even have automation that bounces the cluster whenever the queues fill up. So this is how serious the problem is. You can, of course, keep elevated latencies for more or less forever, assuming like you will still have this constant arrival rate, or you can try increasing concurrency, can try bouncing nodes, whatever. In Little's law, this will be reflected by reducing the request time. Or I think what we should ultimately do is shed the load. We can be smart about what specifically we're going to be shedding, so let's try to figure the rest of it out. So in a majority of cases, the major factors that are contributing to clogging and that can sort of like instruct us what specifically we should consider when considering like what type of requests we're going to be shedding is, so the first one, either we have like uniform increase in the request rate, in which definition of fairness is going to be like randomly selecting the queries that are going to be shed. The second one is there is a change in request pattern, in which case we will try maybe preferring one request type over the other. And the third one is a change in request rate or request pattern for a subset of clients, in which case the likely preference is going to be not to starve majority of clients just for the sake of one. But okay, I'm probably going to skip this one just for brevity, because I really want to get to the way forward. So we've spent a lot of time talking about things that are seemingly simple, but I think that it was important to set up the stage for the rest of the discussion. So I feel like whenever people are talking about database internals, they always talk about, B trees versus LSM trees, Paxos versus Raft, and this compaction strategy over that, and so forth. I may have contributed to that. Sorry. While these things are important, I feel like there are other things that we need to pay great attention to in the database to make sure it is stable and easy to operate. So with 4.0, we've made Cassandra the database that you can deploy from 0.0 release. That's great. With 5.0 and 5.1, we're bringing it to the next level and at very least to parity, and in many ways making it much greater than a lot of competition. But there are still many things that we can improve upon, and cluster stability is definitely one of these things. So I'll try to share some of the ideas I had with the contributions from some of my colleagues, primarily Benedict Elliott-Smith and Abe Ratnowski, who's here in this room, whom we have discussed these things with. To sum up, so far we focused on the fact that it is important to consider all aspects of the system that contribute to latency, including queuing. And then we discussed that queuing can, especially during load spikes, become a major contributing factor, and that we need to find a way to shed the load. Let's now discuss some of the strategies. How do we collect information about what requests can be shed away, and how do we do that with a minimal impact for the cluster? So most of the talk is going to be trying to focus on fairness, and let's try to first talk about how one request may be different from the other one and what kind of guidance that can give us. So first example is a client that starts dominating the load. So this can happen due to, for instance, misconfiguration or some bug in routing several layers above the database, or maybe during to denial of service attack or sudden increase in traffic from a single source or several correlated sources. So if requests from one or a small portion of the clients start to overwhelm the cluster, they'll cause latency spikes for the rest of the clients. So if clients have different expectations about how long it's going to take or how long it is allowed for the request to be processed, and they often do, we are definitely not doing a right thing by ignoring this information or this aspect or this knowledge that the client has. So moreover, in many cases, requests from a single source have at least some sequential nature. So client has its own maximal throughput, you can say. And spacing the responses a little bit from one another will not necessarily cause any service degradation for this specific client. And it will make it possible for us to substantially improve the situation for the other clients. So one argument against having a distinction between different request types is that users may not necessarily prefer to have their reads being dropped in favor of writes or vice versa. But we are already doing this. We currently have only one request intake, and threads that are picking tasks from the queue are blocking, waiting on the replica responses. Meanwhile, on the replica side, we have read and write stages, each backed by its corresponding queue. So you already can easily end up in a situation where an aspect of the workflow on the replica side is completely overwhelming the rest of the request types. A clogged read request queue on the replica side, which can be either a result of reading through a large partition, misconfigured number of threads on the read stage, can easily clog up the native request queue on the coordinator side. So, however, I think that if we implement fairness between clients, there will be many use cases that will require us to make a choice between dropping a read and dropping right when the server is overwhelmed. And I think that this is a right call ultimately, and we should all sort of like start accepting this slowly. In the majority of cases, all production traffic is not equally important, and one of the ways we try to service all requests is by deprioritizing the requests for workloads that have higher deadlines set. So imagine a situation where we have a set of clients that might be serving different purposes. Some of them might be processing customer-facing requests. Let's say a single customer-facing request fans out a dozen requests to the database, but a web server making this request can only process 10 requests at a time. That means that at any given point in time, there can be at most 120 requests coming from that server, even if requests do not depend on one another. In other words, results from the previous query aren't needed to execute the next one for that specific client. We still have natural rate limiting in some form. So releasing some of that pressure from the database by simply giving every client a fair share of the workload may serve as a natural rate limiter. So remember, the same way we needed to remind ourselves about the queues on the replica and then on the coordinator side, we can say that there are like queues all the way up. And here I've tried to demonstrate the workload coming from 16 clients. Each client gets 16 requests per cycle. Requests here are represented by squares, and the color indicates which client they belong to. So for each client, requests are coming at a different rate, which means that their allocation will be depleted faster or slower. If we keep replenishing allocations for all clients at the same time, time will be sliced fairly among these clients. An important remark here is that it doesn't mean that we will throttle the client even if the server is idling. Of course, we will try to process as many requests as we can, whatever the backlog is from a single client, and we just don't want to do this at the expense of the other clients. We will only shed the load when the server is at capacity and we simply cannot take any more load. So in principle, there are two ways we can approach this fairness problem. So we can do this either by splitting queues or by prioritizing items within a single queue. Or we can use some form of a combination of these two approaches. Queue separation is a quite simple thing. Instead of putting things that match different criteria into a single queue, we separate the queues and pull the items from the queue according to some algorithm. We can discuss some of the examples later. One problem with the split queues is that we were to split by every single dimension that we have discussed today or that we can conceive. We would end up in a situation where we have so many queues that we're going to be overwhelmed ourselves as developers, and the server is going to be trying to figure out which queues to pull from. And it all has its own problems and inefficiencies. And while it may make sense to split by some of the dimensions, we'll have to use prioritization for the rest of the dimensions. For example, we can do this by deprioritizing some of the requests towards hot partitions or allow replica sets that serve them to catch up. Potentially also bring some of the resources for like maintenance, like compaction and stuff. To fairly distribute pulling items from the queues, we can use some form of a token-based or leaky bucket-based rate-limited algorithms where each queue gets an allocation of items it is allowed to consume before we can continue pulling items from it again. And these tokens get replenished as soon as we are able to allow other queues to get represented fairly. If the queue reaches capacity, and again, capacity here is not determined by the number of items, but rather by theoretical possibility to get to process this request. If, based on the number of items and recent processing times, we won't be able to process this request, or if we know that the time that items pulled off the queue already close or past the timeout, we can respond to the client and notify it that request will not be processed and should be retried. So queue prioritization can be important, first of all, because of the hot partition problem. If a single partition dominates the workload, it can starve traffic directed to anything else on the same node. and have substantial negative impact on coordinators that have outstanding requests to the same replica set. So first, read and write queries on the replica set become congested, then the negative effect propagates to the coordinator side, and so on and so forth. So the trickier question here is what to do with latency imbalances. What if some queries are several orders of magnitude slower than the other ones? Should they be allowed to head-of-line block other requests, or should they get somehow deprioritized to minimize their impact? Most likely, finding a reliable mechanism to detect a potentially slow query, some form of, I don't know, cost-based workload balancing will be prone to error and may cause more harm than will do good. But if the latency imbalance is caused by a slow replica or replica set, deprioritizing traffic towards it, in addition to avoiding negative impact other queries, may also help us to help this replica to recover quicker. So probably the best example in this case is an analytical workload, such an ETL job that is running concurrently with the regular day-to-day traffic. So such workloads may have bursty nature and a tendency to throw as much at the server as possible. However, one can definitely state that these workloads have lower priority than customer-facing traffic. First of all, because these jobs are usually running for a long time, and making them a little bit slower isn't going to make that much difference in most cases. Here, I've tried to represent threads in the system by vertical lines and distinguish between the request types by color. Line length represents query duration, and you can see different request types interleaved, which means that different workloads may exhibit strong influence on one another, and spike or change in one may cause a disruption in the other. Contrast this with when the requests that belong to different workloads have completely different or separate queues. In this case, we can still share resources for processing queries in these queues, but we can maintain fairness among these different workloads by not letting a single one of them dominate. So it is debatable whether or not we should shed reads over writes or vice versa. Most likely it will depend on the situation at hand. However, if we allow clients to tag their workload in a particular way, for example, to draw a distinction between an online and offline jobs, primary or secondary queries, we can use this information to prioritize requests on the replica side. And it doesn't mean that some of the traffic is going to be always slower than the other traffic. It just means that during the catastrophe, we know what to do with this traffic. What are some of the health metrics that we can use for prioritizing the request? So response latency and change in its trend is a great proxy to gauge the node health. If latencies are trending up, there is a chance that the node might not be able to keep up. However, without additional information from the node itself, it might be difficult to know whether the trend is accidental or action. So replicas can share their internal statistic or interpretation of their health with other replicas and coordinators, and these can be used to deprioritize requests towards unhealthy replicas to give them some time to catch breath. This information can also be used for failure detection. Having like a live dead status, like binary one, is only the first approximation of the node health. Knowing that the node is overwhelmed and a more nuanced metric can help to avoid failure detector flipping between alive and dead and make the recovery from that state quicker. So based on how recently the health information was updated for the node, we may discount it. In other words, more recent information should be considered more relevant and should have more weight. Coming back to the topic of client improvements, we should extend native protocol with new features that will make sure the clients can react to changes described in this talk. Probably the most important feature is client-provided deadlines. Deadline should be driven by the client, since it is the ultimate target of all the database operations. Clients can provide deadlines on the session request or request base, it doesn't really matter, and they can inform coordinator about when the request has started. since we cannot fully trust remote timestamps, we'll need to make sure that the client-server clock drift is small enough to be ignored, and is definitely several orders of magnitudes smaller than the timeout itself. So currently, clients receive overloaded exception when coordinator is in the process of being bounced. I think that we need to give the coordinator an ability to send "I am going away" message, which would not only retry current requests by the client on the other nodes, but will also avoid this node for all the future requests until it comes back. This is happening up to a point with the gossip propagation to the client, but it's not 100% reliable. Another thing that we have already discussed, but it's worth repeating it in this context, is the concept of safe retry. Coordinators should be able to relay to the client the fact that the request has not, in fact, been executed and is safe to have it retried. In many cases, we can issue this response preemptively before waiting until the timeout. Client's backup story also can be improved. There has to be a mechanism to instruct the client about the overwhelmed database that would make it back off slightly. However, if we implement client-set deadlines, TCP backup is going to become an option again, and we may not even need to implement this. So now we're coming probably to the most ticklish questioning of the entire talk: load shedding. No one likes shedding the load. Only bike shedding. Maybe this is why the ultimate deadline for any request in Cassandra was implicitly expressed by 12 seconds of default sockets timeout for years. But as we have seen, we do need to shed load from time to time. And if we do not approach this scientifically, we will shed simply some load or do it in inopportune moment, or we may overload or even crash the node. So our existing protocol does not allow to give a prompt failure response that instructs the source of the query to try on the next available server. And this logic can be applied both to coordinators and replicas. Right now, on the replica side, on the client side, we are relying on the fact that some of the requests are idempotent, and then we can try retrying them. So I think that we should have both please retry on a different coordinator and please retry on a different replica, and both of these responses could be given to the corresponding client or the corresponding coordinator preemptively, meaning that before we have gotten to execute request and it's way too late to even try to retry. So now we're gotten to dream big territory. What if you never have to pick a number of threads for any of the thread pools, or okay, at least for these 3 thread pools. Let's not dream too big. So moreover, what if we could rebalance the number of threads on these stages dynamically? Do I hear somebody saying this several hours ago? I think maybe yes, maybe not. So moreover, yeah, we should definitely at least try to do that. Well, we can feed the queue depth, the arrival and processing times all the way back to the system and let it size the queues correspondingly. So we need to become much smarter about scheduling maintenance and about trying to perform the resource-intensive tasks in off hours. So most clusters do not have steady load against them, and taking pattern fluctuation into consideration will help to improve stability and resource utilization. And if the change in the load or load trend is permanent, we can use something like a dynamic range handoff. With a transactional cluster metadata, we can split off an arbitrarily small range of the replica set and hand it off to either another replica set that is idling or a new one completely. One more problem that we could fix rather quickly is to reduce the window of over-replication. Right now, if the node owns a token and has a replication factor of 3, there will be 3 huge ranges streamed during Bootstrap. However, this doesn't have to be this way. So we can hand off ranges in smaller increments, reducing the amount of time each individual range is over-replicated. And my ultimate dream is, of course, to have elastic clusters that can be scaled up or down with minimal involvement from operators. And we can simply have like a pool of nodes to hand the ranges off to. And yeah, we should definitely try doing this. So let's think to tackle. Yeah, this is exactly one thing for this one thing, but which will remain outside of the scope of the CEP proposal I was working on, is to make sure that maintenance doesn't starve reads and writes. This also sort of like circles back to this SEDA sentiment that I heard a couple of hours ago. We need to become much better about how we are. Okay, now I think I'm out of time. How we're handling maintenance. So this includes handoff, repair, and bootstraps and replacement. So the bare minimum for that is to allow operators to hook their to react to the information on the queue changes in their automation. I think that should be done. And that was more or less it. I'm very glad that I skipped at least one slide to win us some time. And there is going to be a CEP. I almost published it by the time of this talk, but not quite. But it's going to be coming very soon. And I don't know if we do have time for questions or not. But if we don't, I'll be taking them outside. Now
one question only.
One question. Yes, please.
I don't know my best, so I'm not sure I'm pick.
Yeah.
I have one question. The first part was about the request queue. Is the request queue on the coordinator shared with the replication host? Like,
Right.
Do they share the same?
Right now, these are two different queues right now. And I don't think we should conflate them either. Yeah.
I agree. It's like something I learned recently. I didn't notice. That's part of the second question. Is that I didn't know you can run in like coordinator mode. So
In principle.
In principle. Okay.
Yeah,
I
I
know.
know.
In concept, isn't that part of the answer? The elasticity, just to add more coordinator only.
Like, I don't know. Historically, Cassandra was not very like, we never wanted to have different kinds of nodes because it makes everything more difficult to operate. And I think this is ultimately, at least at the current way we're implementing things, is maybe not the best approach. So this is not something I'm going to be pursuing, but it doesn't mean that the other people shouldn't be trying to pursue that. So maybe there is at least some sense in trying to have like fat clients or like coordinator only nodes. But I think that we can do just fine without them if we size the request queues, the thread pools appropriately and react to the changes in the queue sizes by resizing or like shedding load or resizing the thread pools. Thank you very much.